Hi everyone, this is Kevamshi from ECD session. So today I want to discuss about the linear system identification in a non-linear setting. So coming to the topic, linear system identification is a basic step in modern control design approaches, starting from experimental data. A linear dynamic time invariant model is identified to describe the relationship between the reference signal and the output of the signal. At the same time, the power spectrum of the unmodeled disturbances is identified to generate uncertainty bounds on the estimated model. Linear system identification is also used in other disciplines, for example, vibrational analysis of mechanical system, where it is called as model analysis. Because of because linear time invariant models are basic model structure, linear system identification is frequently used in electrical, electronic, chemical, civil, and also in biomedical application. It provides valuable information to the design engineers in all phases of design process. So starting from the late 1916, system identification tools have been developed to obtain parametric models to describe the dynamic. So here you can see the graph describe the sweep frequency and amplitude and instantaneous frequency dynamic behavior of the system. A formal framework is set up to study the theoretical properties of the system identification algorithms and efficiency are more analyzed in detail. Underlying all these results are the assumption that system to be model is linear and time invariant. The focus is on non-parametric block black box identification methods. However, the results might also be useful for physical modeling methods. Knowing the actual nonlinear distortion level can help to choose the required level of detail needed in the physical model. So for this a we can see the example for the motivation. So electronic circuit mimics a nonlinear mechanism system with a hardening spring. Such a system is sometimes called as a forced dumping oscillation. This class of nonlinear system has a very rich behavior, including regular and cyclic motion and generation of subharmonics. The system is excited with an input u of t, where u of t is a unit step function. The output of the system corresponds to the displacement. It is denoted by y of t. The system can be schematically represented as a second order system with a nonlinear feedback. It is excited with low pass random excitation with maximum excitation frequency of 200 Hz. So here you can see the diagram for the frequency representation, in where figure 1 denotes the a forced dumping of oscillator, and where figure 2 describes the system is excited with a low pass signal with a maximum excitation frequency of 200 Hz. So modeling the nonlinear system using linear system identification tools. A linear approximation model will be estimated to describe the input output relation of the system from the flat tail part. The tail is a split in 10 superchords with a length of 8692 points, and each of this is used to identify the second order discrete time plan model and sixth order to noise model using the Bok Jenkins model structure of the prediction method. The estimated second order plan transfer function. Using this model, the output is simulated, which is identification term used to indicate the output is calculated from the measured input. The simulation error, which is difference between the simulation method output, is shown as in the figure 5, which is in the above, and which is in time domain, and figure is frequency domain. For the last super record subrecord, the latter shows all the 95% amplitude bound of the simulation error that is calculated from the estimated sixth order noise method model. So here you can see the diagram for the amplitude spectrum of the input and output signal, which the spike at 250 Hz is a harmonic disturbance of the maze. So from these results, it can it can be concluded that a linear model still gives a reasonable approximation of the output of the nonlinear system. Moreover, the power spectrum of errors is well captured by the noise model, even if the dominating error is, in this case, the nonlinear distortion of the system. That part of nonlinear distortion that cannot be captured by the linear model is added to the noise distribution in the linear identification framework. The whiteness at rest of the residual in figure 7 shows the Estimated noise model describes well the power spectrum, but from the cross correlation, the step between the input and these residuals, it can be seen that there are still more some unexplained linear relation. Observe that the largest spike occur at negative lags, which indicates the need for non-causal terms in the BLA. Since the identification of is not done under closed loop conditions, this behavior can only be due to the nonlinear nature of the system and validation of the linear model. In the second step, the identified linear model is validated on the arrow-like part of the order. This is a challenging test because the excitation level on part of the data exceeds that of the peer that is used to estimate the linear model. From figure 8, it is seen that the errors become very large once the excitation level exceeds that of the tail part. The approximate linear model fails completely under this condition because it can capture the underlying nonlinear behavior of the system outside the domain where it was fitted to the data. So also analysis of the model uncertainty. The estimation procedure resulted in the plant and noise model. From this information, it is possible to also obtain an estimate of uncertainty on the results. In figure 4, the estimated standard deviation of the transfer function is compared with the sample standard deviation calculated from the repeated estimates on the 10 sub records. Both curves look very similar, but the model based estimated value underestimate the actual observed standard deviation. So the user should keep in mind that the confidence bounds are wrong whenever they are used during the design. So coming to the detection, verification, quantification of the knowledge decisions. In this section, tools will be presented that allows the user to detect and analyze the presence of the nonlinear distortion using the initial without needing more explanation experiments. That FRFBL of the power spectrum of the distributing noise and the level of nonlinear distortion will be obtained. So it describes about the detection, qualification and quantification of the nonlinear distortion and the coming to the response of a nonlinear system to a periodic excitation. A linear time invariant system that cannot transfer power from one frequency to another. In contrast, a nonlinear system can transfer power from one frequency to another. Understanding this power transfer mechanism is an essential tool in the detection and analysis of nonlinear distortion. Considering a cosine signal passed through a cubic static nonlinear system y equal to uk. So here you can see the Stanley periodic form and also the signal has a positive and negative frequency. The steady state output of the nonlinear system is shown by y of t equal u of t whole cube. So also design of multi-design for nonlinear detection and frequency response function measurements. The choice of the excitation signal is extremely important in nonlinear framework. The behavior of nonlinear system depends on the both power spectrum and the amplitude distributed of this applied excitation signal as shown in figure 20. In this article, signals with a Gaussian amplitude distribution will be used. Gaussian random noise excitation are very popular among the practicing engineers because they seem to be simple to design. However, in this article, periodic excitations are used because these signals offer significant advantages for making a non-parametric nonlinear distortion analysis. It will be shown later in this article in this section on Riemann equivalent excitation signal that the results obtained from the periodic excitation can also be transferred to random Gaussian noise excitation from proper normalization. So here you can see the graph related to the noise, Gaussian noise, periodic noise and random multism. So coming to the characterization, nonlinear distortion under closed loop conditions, it is an extended framework. As explained before, two problems are faced to deal with measurements under the closed loop. The FRF measurement is biased and the second actual excitation of UFT. So the below information related to the characterization of non-linear under closed loop condition. So it is based on two conditions, like the FRF measurement is biased and actual excitation signal of UIT. So here figure 36 describes the nonlinear distortion analysis at the output of the op-amp before and after the software elimination of the feedback effects. So here you can see the amplitude dBB of one signal and another signal which had different frequencies, different range of amplitude according to the frequency change. So coming to the forced duffing oscillator, the measurements on the forced duffing oscillator which are discussed earlier are the further processed. The FRF is measured for the four different excitation level. The FRF is also is averaged over 50 realizations of the input signal to obtain a smoother result. Observe that the resonance frequency shifts to right for increasing excitation levels and that measurements become noise. Both effects are completely due to non-linear distortion. The level of distortion correspond to this measurement. So ground vibration test on 5 touch. It is an example for the above topic that the measurement of a ground vibration test which was discussed earlier are processed. In this example, some additional signal processes were done to provide additional information. This leads to an alternate method to detect and analyze the presence of nonlinear distortion called this a robust method. For each realization, the FRF is average over the successive period. This provides a not only average FRF, it gives also an estimate of distributing noise variation where it denoted by y of k as a function of the frequency. This estimate is all not affected by nonlinear distortion because they do not vary over the other. So thank you. Have a nice day.